Hello everybody, and welcome to part B of example 3 on page 81 here. So, just to refresh your memory, the instructions are on the previous page. They're giving us a generating set G for the vector space V that we have here. So in this case, V is the set of symmetric 2x2 matrices with entries in R. Okay, and G is a generating set, and our goal is to find a basis for V. Okay, to take that set G and, if necessary, remove enough of those matrices so that we have a basis. Okay, so we're going to approach this the same way that we approached the problem in the last video. So we could do this problem using previous techniques if, instead of having a set of matrices, we had a set of tuples. Okay, so what we're going to do is to choose a basis for V and to replace the set G with a set of coordinate vectors. All right, so we have kind of a nice basis that we generally use when we talk about symmetric matrices. You might remember it when I write it down. It looks like this. Okay, so 1, 0, 0, 0. 0, 1, 1, 0 is our second one. And 0, 0, 0, 1. Okay, remember a symmetric matrix, again, is just a matrix where it equals its own transpose. So all of the matrices in G are symmetric because these two entries are the same, okay, in all of those matrices. Okay, so there's our basis, and then G prime is going to be the set of coordinate vectors of our matrices one at a time. So if we start with the first matrix 1, 3, 3, negative 2, the question is, how do we build it as a linear combination of the vectors in beta? Okay, well, we can build that by, let me give myself a little bit more space here. Okay, I'm going to write these vectors in column form. Okay, so 1, 3, 3, negative 2, we could write by taking 1 times the first matrix here, plus 3 times the second matrix here, plus negative 2 times the third matrix here. Okay, so we get 1, 3, negative 2 for our first coordinate vector. All right, and then we move on to this, and similarly, that's going to look like 2, 6, negative 4. Okay, those are the coefficients on the three matrices in beta that we need to build it. Okay, and let's just go ahead and list the rest of them. Negative 3, negative 8, and 8. 1, 3, negative 2. And negative 2, negative 7, and 1. Okay, I'm just going to take a second and make sure I copied all of those down right here. Okay, 1, 3, negative 2, yeah. Okay, and the idea is there's an isomorphism between V, our vector space, and R3, because these are coordinate vectors in R3. So what we can say with confidence then here is that G prime is a generating set for R3. Okay, and if we can reduce that generating set for R3 to a basis, then that's going to tell us how to reduce the set G that we were given to a basis for V. All right, so what we'll do is we'll form a matrix, okay, with having its columns the same vectors that we just wrote down. Okay, so this is a little bit tedious having to do all of this writing and rewriting. 1, 3, negative 2. Okay, and then negative 2, negative 7, and 1. Okay, let's just take a minute and make sure I copied all of that right. Okay, and then do row reduction on this. This is probably easier done with a calculator or something. Okay, I'm just going to show you what I got after I did row reduction here. Negative 3, 1, 0, 1, 0, 0, and negative 2, negative 1, negative 1. See if those are right. Okay. And it comes down to where the pivot positions are. Okay, so we circle those. There's the first non-zero entry, another one, and another one there. So we've got pivots in the first, third, and the fifth columns. Okay, so kind of marking those in our original matrix, that means that those three columns in our original matrix would form a basis for R3. Okay, so beta prime equals, I'm going to write them in row form this time. 1, 3, negative 2, negative 3, negative 8, and 8. And negative 2, negative 7, and 1. Okay, that is a basis for R3. And now, because of the isomorphism that we mentioned, that tells us which matrices we should take to get a basis for V. Okay, so starting with this first coordinate vector, that was the coordinate vector which went with matrix number 1. Okay, this coordinate vector went with matrix number 3, and this one with matrix number 5. So we need to take the first, third, and the fifth matrices, and that should give us a basis for V. Okay, so last step is just to write down those matrices, and then we've got ourselves a basis. Okay, there is our basis for V. Okay, so just to kind of reiterate the strategy here, what we're doing is just taking our problem and kind of translating it into a problem in tuple land, R3, using what we learned back in chapter 1, I think it was, and then just converting back and getting the basis that we really want.